Okay. Okay, so this is actually a course which I taught 4 or 5 years ago. I'm going to make some change along the way, independent on your interest, and just because now some things have become more important than they were at that time. They were just beginning, and now they are extremely important. That's probably, I guess, one reason many of you are joining this course is because you are interested in topology and the interplay with symmetry. So I'm going to orient the course in that direction a bit, okay? So, well, to begin with, let me see how this works. Yeah, why group theory? Why should you learn, or is it a good idea that you learn theory? Well, there are 2 reasons mainly. The first reason is that it's extremely powerful technique. Basically, it deals with symmetry, and it lets you extract all the physical consequences of the symmetry of a system reliably and efficiently. So all the consequences in a very reliable and efficient way. Probably all of you know how to extract consequences for the symmetry, but if you don't know group theory, you may be missing consequences or you may be doing it wrong. So group theory is very efficient and very powerful. And it's extremely simple theory. It's one of the simplest things that you can learn. Basically, all you have to know is the 4 rules. You have to know how to add, mostly integers all the time, divide, subtraction, multiplication, and know a little bit about matrices. I mean, this is completely unlikely other things like many-body theory, quantum field theory, which are extremely demanding technically. Group theory is I mean, little children could learn it very easily. The fact that it's simple doesn't necessarily mean that it's easy, okay? These are different concepts, as you will see. Well, what symmetries are we interested in? Well, there are 2 types of symmetries. First, you have space-time symmetries like rotations, translations, parity. Parity is inversion, space and inversion. Time reversal symmetry, Lorentz boost, Galileo boost. All of these things play a role in condensed matter physics in different areas. And then internal symmetries like SU2 isospin, SU2 U1 of electroweak interaction, SU3 color. You see that most of these things are really for high energy physics, okay? These are different symmetries. In condensed matter, we'll be concerned mostly with space-time symmetries, inversion or parity, time reversal, rotations, and translations, okay? Well, there is another classification of symmetries. Besides speaking of space-time symmetries and internal symmetries, you can consider continuous symmetries, and like SO3, SU2, all of these are Lie groups, basically they are called when they are continuous symmetries. And then the kind of group theory techniques are peculiar to these kind of symmetries. You use Lie groups with Casimir's roots, Cartan subalgebras, linking diagrams, Young tableaus. Some of you may be familiar with this from some particle physics course or high energy course. We won't use any of this kind of group theory, nothing at all, okay? We won't need it. We'll just need to know what the irreducible representations are for the rotation group, and this is very simple without need to use any of these techniques. And then we have discrete symmetries. I mean, in solid state, a crystal usually has discrete symmetries. Only a discrete set of translations leave the crystal invariant, only a finite number of rotations leave the crystal invariant, etc. And then the techniques are completely different from the continuous symmetries. The central concept is the one of character, orthogonality of characters, projectors, things like that, that we will see. So basically, we are going to concentrate on this kind of group theory. Basically, we will always be dealing with discrete subgroups of O3, the complete group of rotations, including mirror symmetries and inversion, lattice translations, and time reversal symmetry. Okay. So far, I mean, so good for the symmetries. Now, what kind of consequences do we want to extract? Well, when you deal with continuous symmetries, this is the sequence. Symmetries, by Noether's theorem, implies conservation laws. And then from conservation laws, if you are doing quantum mechanics or you are doing small oscillations or dynamical matrix, you obtain degeneracies and selection rules plus many other things. Okay, these are the more obvious. Now, when you have discrete symmetries, there is no Noether's theorem for discrete symmetries. Discrete symmetries do not imply conservation laws at all. So you have to jump directly from symmetries to degeneracies and selection rules. And that's the reason you need a group theory. I mean, if you have a conservation law, you can obtain the consequences very easily, even if you don't know anything about group theory. For instance, you already did this in your first or second year of your undergraduate studies. For instance, when you consider the two-body problem or the planetary system, the sun plus a planet, due to the fact that the field created by the sun is spherically symmetric, you have conservation of angular momentum. And from angular momentum, you can obtain that the orbits have to be planar, and you obtain immediately the area law, the Kepler's area law. Okay, but basically what you use is the fact that angular momentum is conserved. Probably the first time you saw this, the teacher didn't even emphasize the symmetry. He just said, oh no, angular momentum is conserved, and from there you go on. Okay. However, if you don't have absent conservation laws, then you really need group theory. Okay. So let me remind you how you did it for spherical symmetry. For spherically symmetric systems, angular momentum is conserved. Why? Because being a symmetry of the Hamiltonian, it commutes with the Hamiltonian. Okay. And now, for instance, when you study the hydrogen atom or any spherically symmetric potential, not necessarily Coulomb, you obtain this thing for the matrix elements. For instance, you prove that the Hamiltonian cannot connect states with different L or different M, and moreover, you prove that the matrix elements can only depend on L. It doesn't depend on M. How did you do that? Well, basically, all you have to do is to take this, that the commutator of H and L is equal to 0, and then write a ket here and a bra. Basically, for instance, if here you place LZ square, you immediately obtain this. If here you play LZ, you immediately obtain this. To obtain this is a bit tricky. I don't know if you remember, you have to use the rising and lowering operators, angular momentum operators, L plus and L minus. But basically, it means that you extracted all the consequences just from this, from the conservation law first, and then second, from the algebra satisfied by the components of angular momentum. Okay? So you didn't need any group theory. Okay? Similarly, you extracted selection rules. Basically, the first thing is a statement, the one you can see my pointer, I guess. Here, this is just a statement about matrix element of the Hamiltonian. The selection rules are a statement about matrix elements of perturbations. For instance, this is the selection rule for dipolar electric transitions in an atom. Delta L has to be necessarily plus or minus 1. This is for dipolar magnetic transitions. Delta L has to be equal to 0. And basically, what you do is you compute the matrix element instead of H, just the perturbation. I mean, in the dipolar electric approximation, this will be the vector potential A times the momentum operator P. Okay, more complicated things for this. So basically, you could do without group theory. Now, why is this a problem for discrete symmetries? Well, you have to remember how you got how you went for continuous symmetries like spherical symmetry from the symmetry to the conservation law. Basically, remember that in quantum mechanics, an SO3 rotation can be written like this. This will be a vector parallel to the axis of rotation, and this is the angular momentum. And then this is a symmetry. The Hamiltonian commutes with the unitary operator. Okay? Why? Because after I transform the Hamiltonian, I get exactly the same Hamiltonian because nothing changes. Obviously, the kinetic energy is invariant under rotation, and so is a potential which is spherically symmetric. So from this, if I expand, I mean, the point is that this is a continuous symmetry, so this is valid also for infinite angle. And I keep linear order in the angle. If I substitute this thing here, I immediately get the commutation and the conservation law. So that's another way of looking at Noether's theorem, which is not so general as Noether's theorem. Noether's theorem is valid also in classical physics. But basically, the point is that for continuous symmetries, I can go from the unitary operator for finite rotations to the infinitesimal generator. For those of you who know anything about Lie groups, I can go from the group to the Lie algebra. L is are the generators of the Lie algebra. Okay. For discrete symmetries, this is valid only for a finite set of rotations, not for infinitesimal rotations. So I cannot do the previous operation, and angular momentum, of course, is not conserved. So this does not imply this commutation relation. Entonces, we miss the essential link between symmetries and consequences, which are the conservation laws. So this is our situation. For continuous symmetries, we have this. I don't know if I can move this thing away from here. Okay, now for discrete symmetries, we have a big jump from discrete symmetries to degeneracies, and the parachute is loop theory. Okay, so now this is the outline of the course. If I have time, I will comment on the program later on, but basically, I can tell you that all these things, I mean, the first 5 lectures deal essentially with point groups in different systems, molecules and atoms, basically. And then after the 6, we deal with crystals. There is a big jump. Point groups are a lot simpler than space groups. And the group theory of space groups is much more subtle, okay? So first we have to understand thoroughly the point group symmetry, which after all is also present in crystals, before we can move to space groups. Then we'll apply this to electron bands to find the irreps, to study, to see the compatibility relations and that. And then in the last lecture, we will see the relation between group theory and topology. Basically, we will apply the techniques of topological quantum chemistry to the honeycomb lattice, both to phonons and to electrons. Okay. So now for the introduction. So this is the methane molecule. This molecule is very symmetric. You know that the hydrogen atoms are at the vertices of a tetrahedron. So it has a big symmetry group. It has 24 elements. Probably you all know. And of course, this big symmetry group has an impact on the spectrum, on the vibrational spectrum of methane. Now, the question is the following. Can we say anything about the spectrum just by looking at the molecule? By the spectrum, I mean how many frequencies we have, are there any degeneracies, things like that, okay? Well, we can say a little. First, there are 5 atoms, 4 hydrogens and 1 carbon. So, since each atom can vibrate in 3 directions, I have 15 degrees of freedom, okay? If this is the molecule in equilibrium, if I give a different displacement to each of the atoms, this is described by a 15 components vector. I give first the three displacements, I mean, the three components of the displacement of the carbon, then of this, or this. This is a total, is a vector of 15 components. So if I want to study the vibrations of this thing, I have to set up in the harmonic approximation. I have to compute what is called the dynamical matrix. It's just essentially the potential energy matrix. It's not exactly, I'll review that later on. But basically, I have to diagonalize a 15 by 15 symmetric matrix. So, in principle, since this is a symmetric matrix, I can always diagonalize it, and I have as many eigenvalues as the dimensions. So in principle, I can get 15 frequencies. But that's not the whole story. The 15 by 15 symmetric matrix is not generic. It describes the dynamics of a molecule. And now a molecule is a very special object. Out of these 15 degrees of freedom, 3 correspond to rigid translations and another 3 to rigid rotations. For instance, if I give exactly the same displacement to all the atoms, this is just a translation. Of course, there is no vibration. Why? Because I haven't changed the relative distances. If I don't change the relative distances, I haven't really perturbed the chemical bonds. The molecule doesn't vibrate. The same thing happens if I rotate the molecule around the center of gravity. This is a bit more complicated, but it's the same story. So this means that I have 6 zero modes. The 6 zero modes is another way of saying that for some special combinations of translations or of displacements of the atoms, the associated frequency is 0. So I know that even though I'm diagonalizing a 15 by 15 symmetric matrix, only 9 frequencies are going to be different from 0. The others are 0 frequencies, and the corresponding normal modes are called 0 modes. Okay? So this is as far as we can go without taking into account the symmetries of the molecule. This is valid simply because it's a molecule, a non-linear molecule, by the way. The counting is slightly different from linear molecules, but I won't mention that anymore. Now, this has a lot of symmetry, but can anybody, just by looking at the molecule, tell how many frequencies are going to be degenerate, how many frequencies are going to be different, etc.? Well, if you know group theory, you can easily, and when I say easily, I mean this is a back of the envelope computation. You have an envelope and a pencil, and in 4 or 5 minutes, you can say as much as this. Well, you need tables, okay? You need group theory tables. Basically, you can say, with no question at all about it, that there is going to be one frequency which is non-degenerate. So one frequency with degeneracy 1. Another frequency which degeneracy 2. And 2 frequencies with degeneracy 3. This is a direct and unavoidable consequence of the symmetry of the molecule. You can say even more things. You can say that there are total 4 different frequencies. 1, 2, plus 2, 4 different frequencies with some degeneracies. Well, you can use group theory to know that all 4 frequencies can be measured using Raman spectroscopy. They are Raman active. And also, you can say that only the triply degenerate frequency is infrared active. I mean, Raman spectroscopy is relatively complicated. You need a good equipment. Infrared spectroscopy is a lot simpler. But only you could only measure the frequency of the triply degenerate frequency. All of this is essentially a very, very simple computation involving only integers, sums, and divisions. Okay, so now, we have to know how to do this. That's the way we are going to learn it. Well, now there are 2 possibilities. I could start to give you theorems define what is a representation, speak about Schur's lemma, and then speak about orthogonality theorems. I need to spend a lot of hours, and then we could move to the applications. So that's extremely boring, at least for me, and I'm sorry, pretty sorry it will also be boring for you. So I'm going to do it in reverse, okay? So basically, I'm going to show you the result of a group theory calculation, and first I'm going to teach you how to interpret it. Then you will learn how to do the computation, and then finally you will learn why you do it the way you do it. Maybe a bit confusing at first, but I think it's a lot more fun. Well, by the way, I forgot to tell that for methane is microwave inactive. In microwaves, all you can observe is the rotational spectrum. So you can measure the moments of inertia, but methane is inactive. You cannot see it, okay? Well, I forgot that I had also this before this, okay? This is deuterated methane. I have substituted deuterium for one of the hydrogens. Now, if you know group theory, you don't have to do all the computations again, because group theory, using a technique that we'll learn very soon, which is called subduction, tells you immediately that the only thing that happens is that the triply degenerate frequency splits into one non-degenerate plus one doubly degenerate. So immediately from this, which is the spectrum for methane, you just, instead of 3, you write 1 plus 2 and you get this. So you have 3 non-degenerate, 3 doubly degenerate, for a total of 6 different frequencies. Now all 6 frequencies are both Raman active and infrared active, and is also microwave active, okay? Well, so now let's go back to the methane molecule, and I'm going to show you what a group theory would do to obtain all this information. First, I give you the result of the main computations. This is the result. Look at it. Basically, there are some symbols here. We don't know what they are, but we'll know immediately. M, V, R, and V. There is an equal, and this is these are linear combinations, but they are only integer linear combinations. That's what I told you, that group theory is simple. Almost a 6-year-old boy can understand it. Just integers, and here, well, some symbols. We only have to understand the symbols. First, these are all statements about representations. So the basic concept in group theory, as we are going to use it, is the concept of representation. What is a representation? Well, this is not a very rigorous mathematical definition. We'll see a more rigorous mathematical definition before the end of today's class. A representation tells you how something transforms under the symmetries of the system. It's a very vague thing, but that's the idea. Each type of object has a representation associated to it, because each type of object, when I use the symmetries, transforms one way or the other. Okay, so, and all these things, N, V, R, V, A1, E, T2, T1, they are all representations. Now, let's try to guess what these representations are. Well, M is the mechanical representation. V is the vector representation. R is the rotational representation. And V is the vibrational representation. Now, usually when you have, for instance, vectors, the vector representation tells you how vectors transform. Now you know how to transform vectors under rotations. You learn that in mechanics and quantum mechanics, everything. You just need to use 3x3 matrices. Why? Because vectors have 3 components and they transform linearly under rotations. So a linear transformation is always represented by a matrix. Okay. So you know now what is the vector representation. It's a set of 3 by 3 matrices, and I have one 3 by 3 matrix for each element of the group, for each symmetry. Well, now, so that's the reason that the dimension is 3, because I use 3 by 3 matrices. That's what the dimension of the representation says. It tells you that matrices are 3 by 3, and it also tells you that these matrices or these operators act on a linear space of dimension 3. What is this linear space in this case? The space of vectors in 3 dimensions. Now, the rotational representation also has dimension 3, and it tells you how pseudo vectors transform. You probably remember from your mechanics or from another course that not all vectors are vectors. For instance, the momentum P is a vector. However, the angular momentum is not a vector, it's a pseudo vector. The electric field is a vector. The magnetic field is a pseudo vector, etc. Vectors and pseudo vectors are very similar. The only difference is how they behave under improper operations of the rotation group. What are improper operations? Mirror reflections and inversion, basically. Okay, so for instance, angular momentum. If I invert the system, everything in the system, so if all the vectors go to minus the vectors, angular momentum doesn't change. Why? Because angular momentum is R wedge product with P. It's a product of R and P. Under inversion, R, which is the position, goes to minus R. P goes to minus P, but L doesn't change. So it's a pseudo vector. The same thing happens with the magnetic field. So, of course, these are also 3 by 3 matrices. They are identical for pure rotations, but they are different V and R when you are dealing with mirror reflections or inversions, okay? Because they transform differently. Finally, well, not finally, M is the mechanical representation. It has dimension 15. Well, you can very easily guess what this means. I told you that a distortion of the molecule can be mapped by a 15-component vector. I just have to say the displacement vector for the carbon and the displacement vector for the 4 hydrogen atoms. So this is a 15 components vector. We'll see that it transforms linearly. So the mechanical representation tells you how general distortions of the molecule transform under the symmetries of the system. So in this case, this is much more complicated, but we'll see that it's only apparently complicated. In reality, it's extremely simple. For each symmetry, I have to construct a 15 by 15 matrix. The set of all these matrices is the mechanical representation. And now, of course, you can guess what is the vibrational representation. I told you that not all distortions of the molecule were pure vibrations. For instance, if I give the same displacement to all the atoms, then essentially I haven't really disturbed the bonds, so the molecule doesn't vibrate. It has 0 frequency. I can give a uniform displacement to the molecule without any kind of vibration, okay? Has dimension 9, that's the reason this is just 15 minus 3 minus 3. Now, if you look at this, we still don't know what this is, what this is, what this is, but the interesting thing that you can already understand is that I obtain the vibrational representation by a subtraction, a formal subtraction of these representations. To the mechanical representation, I have to subtract the vector representation and the rotational representation. Why? Because I get vibrations after I eliminate all uniform translations and all uniform rotations. So if I take this set, and to this I subtract 1T2, I only have 2 T2s. I subtract a T1, I only have 0 T1s, okay? So this is the result for the vibrational representation. You must realize, I've told you that representation associates a matrix to each symmetry element of the group. So we are dealing with matrices. However, this subtraction is not a subtraction of matrices. Why? Because this is a 15 by 15 matrix. This is a 3 by 3. This is a 3 by 3. And this is a 9 by 9. When I subtract matrices, I get matrices with exactly the same dimension. So this concept is not just subtraction of matrices. We'll see that soon, what this really means. Okay. Are there any questions so far? Please, if anybody has a question. Okay. So this subtraction corresponds to this decomposition. Out of 15 15 frequencies, 6 of them are 0 because they correspond to 0 modes, and then I have 9 vibrational modes. Okay, now we know what NVR and VIV are. We still don't know what this, but now you are going to know. These things, you see, there are only these. I told you there are representations, of course, but I didn't tell you what they represent. There are only 4 of them: A1, E, T1, and T2. In fact, the symmetry group of the methane has another representation, which is E2, but for this particular molecule, it doesn't appear here, okay? These are very special type of representations. These are called irreducible representations of the point group. This is the point group describing the symmetries of the molecule. This is the tetrahedral group, and this is in crystallographic notation. This is Sunfly's notation. You don't have to know much about the group so far, okay? And now the important thing is that I'll tell you in a minute what do we mean by irreducible. Well, probably I'll tell you next day, I'm not sure. These are irreducible representations. Unlike these representations, these are perfectly abstract representations. What do I mean by this? These are not abstract. This is describing how the methane molecule transforms, the distortions of the molecule. This is describing how a vector transforms. This is describing how a pseudo vector transforms. This is describing how the space of non-zero frequencies transform. However, they are not telling you how anything transforms. They are completely abstract. They are just associations between symmetry elements and matrices, okay? So basically, if I take A1 to each element of the group of symmetries, it associates one particular matrix. This. But they are abstract. They just exist mathematically. They are also the building blocks of representations. Any other representation can always be written as an integer linear combination with positive coefficients of these basic building blocks. Okay, so you have a kind of a preliminary definition of irreducible representations. These are abstract representations. They don't represent anything in particular. They are abstract, and they are building blocks. Any system, imagine a molecule with 1 million atoms. It's very unlikely that it will have some symmetry, but let's assume that it has some symmetry. Okay, then the representation, the matrices will be 3 million by 3 million matrices, but they can be obtained from these very simple matrices, which are the matrices for the irreducible representations. Absolutely any representation can always be written as an positive integer linear combination of the basic building blocks. Now, these are the dimensions of the irreps. Usually they have small dimensions. I'll tell you for that depends on whether you are considering point group, space group, but they are usually relatively low dimensions. Okay, this is dimension 1, so it means that to each element of the group it associates just one number, because a 1 by 1 matrix is a number. These are 2 by 2 and these are 3 by 3. How do I know the representations? Well, first, all these things are tabulated. Okay, so when you look at the table, it gives you the matrices and that. But even without looking at the table, I know the dimensions for a very simple reason. A and B are always one-dimensional. Since this is a A1, this is one-dimensional. E is always bidimensional, two-dimensional. And T is always three-dimensional in the notation I'm using. I'm using the notation of the Bilbao crystallographic server that I'll teach you how, in the last lecture, I'll teach you how to use it, okay? Well, so now we have to make the connection between this knowledge, which I told you, if you know group theory, you can easily obtain this 1 non-degenerate plus 1 doubly degenerate plus 2 triply degenerate for a total of 4 different frequencies. What is the connection between this and the group theory computation? Well, the connection is this. Look at the vibrational representation. It's the sum of A1, which is one-dimensional, plus E, which is two-dimensional, plus 2T2, which is three-dimensional. And see what I told you about the frequencies. I have 9 frequencies, 1 non-degenerate, 1 doubly degenerate, and 2 triply degenerate. So now you see the correspondence. If this is dimension 1, the associated frequency is non-degenerate. If this has dimension 2, the associated frequency has dimension 2. Since this is dimension 3, the 2 associated frequencies, because this representation appears twice, 2 associated frequencies have the degeneracy 3. So the numbers, I mean, this is always a linear combination. The numbers in front of the irreps tells you how many times the irrep appears. And this is just the number of different frequencies associated with the representation. In this case, since the multiplicity is 2, there are 2 different frequencies associated. Now, the dimension of the representation tells you the degeneracy, okay? Why is that? Well, this is this way because there is a theorem, which is Wigner's theorem, which tells you that this is true. This is one very good reason. But to get to this point, I'm going to recommend you later several books. You have to read several chapters and probably a few dozens proofs and things like that until you arrive at Wigner's theorem, and then you can get more in the way, okay? So now you know the theorem without having to go through all these things. If you really want to use group theory in your work, seriously, you'll have to go to read the proofs and everything, okay? But you may decide later on if you want to use it or not. Well, you can understand this thing partly. Well, no, I won't tell you the argument yet. Okay, but this is the important thing. By doing some operations that you learn how to do next lecture, you will be able to reproduce all of this. And you will be able to arrive at this result. Then the key to interpret the result is just this. Multiplicities, which are numbers in front, are different frequencies associated to that representation, to that irreducible representation. The degeneracies are the dimensions. For the deuterated molecule is again the same story. That's what you would obtain by a group theory computation. The group is different, it's C3V. And then from this formula for the vibrational representation, you see that there's multiplicity 3, so there are 3 frequencies, different frequencies, each of them non-degenerate, and another 3 frequencies for a total of 6, each of them doubly degenerate. Then next time I'll give you, when you know how to compute this, I'll give you a problem set with different molecules where you will practice by doing the group theory computations, okay, and the interpretation of the result. Okay, so now the first thing that you have to understand is the idea of symmetry group. Now, the symmetry group for the deuterated methane is this one, 3M in crystallographic notation, 3CV in Schoenflies notation. This is the group of symmetries of a triangular pyramid. Why? Because, you know, methane is really a tetrahedron. However, if you put here a deuterium atom, this is more like an equilateral pyramid, okay? Triangular pyramid with a equilateral triangle here, okay? It has less symmetry. Why am I using the deuterated molecule instead of the original molecule? Because the group is much smaller. It's a lot easier to explain things with a small group, okay? So this is a view of the pyramid from top, okay? From the top is like this. So for deuterated methane, this pyramid need not be exactly tetrahedron. Probably it is very close to it, but certainly the spectrum reflects the symmetry of the molecule, and the molecule is not invariant under all the rotations that would be invariant the pure methane, okay? The pyramid, you can see, is very easily invariant under 120 and 240 degree rotations, and also under 3 vertical reflection planes. This is broken. And this will be, I don't know what happened. This will be one like this, the other like this. I'll fix that before I put the slides on in the server, okay? So now we are going to study or to see the vector representation for this group, for the group of rotations of the equilateral triangular pyramid. These are the elements of the group. This is broken again, okay? Every group always has the identity operation. This E, you shouldn't confuse it with the representation E. They have nothing to do. It's just a matter of we are using the same letter. Sometimes people use lowercase letter to avoid the confusion. This E represents a symmetry operation of doing nothing. Obviously, if you do nothing, everything stays the same. So all molecules are invariant under the trivial or identity operation. C3 plus, most of you probably know this notation, is a 120 degrees rotation counterclockwise. This will be the same rotation clockwise. And these are the 3 diagonal planes. One goes like this, one goes like this, and another one goes like this, okay? So now the vector representation tells you how vectors transform under these operations. And that's it. Well, this is the identity operation. If you do nothing, of course, the vector stays the same. So you have to multiply your vector by the unit matrix, and you get exactly the same result. If you rotate around the z-axis with 120 degree rotation, you have this matrix. Well, you probably remember it was cosine of the angle, cosine of the angle, minus sine of the angle, minus sine of the angle, 0, 0, 0, 1, okay? For the opposite rotation, well, it's similar. The cosine doesn't change because the cosine is an even function, so you get the same thing, but the sign changes sign. Okay, so with a little bit of effort, you could also obtain these reflections. I'll tell you next day how you do this efficiently. So this is your first example of a perfectly explicit representation. This is the vector representation for a particular group, for the 3M group or the C3B group. Well, the reason I have this here is that this representation depends, of course, on how you choose your axis. Okay, because vectors have different components for different systems of axes. So these matrices in general change if you change your axis. In this case, we have chosen the x-axis to be parallel to this diagonal plane. Okay, this is a diagonal mirror. So if I choose it this way, then you can see very easily how vectors transform under this reflection. Obviously, the z component doesn't change and the x component doesn't change. Only the y component is reversed. If I go back, you see that only the y component is reversed. But of course, this depends on your choice of axis. And that will be very important. That's why I'm insisting on this thing, that a representation is not a unique set of matrices. The vector representation can take many different forms depending on what kind of axis I use. What is essential to a representation is what the linear space is the representation is acting on. In this case, I'm acting on vectors. Well, that's the vector representation. This may change depending on the reference system. Okay. And now I'm going to give you the rigorous definition of representation. The idea is that a representation T of a group G, the group G is the set of all the symmetry operations. I'll remind you later, or maybe I don't know exactly when I organize this, but I'll remind you what a group is. You'll need that to read the books and to, well, every book on group theory tells you the first thing what a group is, okay? But G is the set of symmetry operations. So to each symmetry operations, a representation assigns a linear operator, a matrix, okay? But this assignment is not completely arbitrary. It has to respect the composition rules for the group. For instance, I apply a symmetry operation G2, and then I apply a symmetry operation G1. This is equivalent to applying a single symmetry operation. This is just because the operations form a group. So if G1 composed with G2 gives you G3, the matrices that you associate have to satisfy the same relation. That the product, the matrix product of T of G1 times T of G2 is exactly T of G3. So it means that you cannot assign matrices arbitrarily to the elements of a group, because if you do, you won't satisfy this, and this won't be a representation. Okay. In our case, for instance, if I take a counterclockwise rotation by 120 degrees, and then I take another counterclockwise rotation by 120 degrees, that's exactly the same as taking a rotation 240 degrees or taking a clockwise rotation by 120 degrees. So this means that the composition of C3 plus gives you C3 minus. Then the corresponding matrices have to satisfy this. And you can check that this is true. This was the matrix for C3 plus, again, the matrix for C3 plus. And then when I compose these two things, I get the matrix for C3 minus. So you realize that probably it's not that easy to write a representation unless you have a model. If you know what the representation represents, I mean, what kind of objects the group is acting on, then you can try to deduce what the matrices are. But in general, it's non-trivial. And how many different representations can you write? Infinitely many. Why? Because you can have linear spaces of any dimension. And for any dimension, there are usually very many possibilities for the matrices that still satisfy this. So we have the mathematical problem of classifying all the different, in a sense that I'll tell you soon, the different representations for a group, knowing that there are infinitely many. Okay, so that's what group theory is all about. Studying representations of group and then being able to compute representations and operate with representations. And then, of course, you have to be able to relate this with physical systems and physical consequences. Well, this is an appendix for this part, which is groups. In mathematics, a group is a set of elements with the following properties. There is a composition law. You see, I write this circle to indicate that this is not a product. That depends on the group. For instance, if you are considering the group of translations, if you translate by a translation T1 and they by a translation T2, this is equivalent to translating by T1 plus T2. So in that case, it's vector addition. For different groups, this represents completely different things. Okay. Well, the properties are there has to be a neutral or unit element that doesn't do anything. This is always the trivial symmetry, doing nothing. For each element, there is an inverse. For instance, for a clockwise rotation, there is the counterclockwise rotation, which is just the inverse. And then the composition law is associative. Okay. So here, it's important to realize that here I have some composition law that can be anything, but for the representation is always matrix multiplication. Okay. Even if you consider a group where the operation is addition, like the translation group, the corresponding matrices, you always have to multiply them. Okay. Okay, this is one possible book that you can follow. As I tell you, I mean, if you just follow the course and do the exercises, what you will be able is to read papers where group theory is used. You will understand what they are doing. Okay. If you really want to be able to do it and to use it in real research, you should study one book. For instance, this one, when I first gave this course 4 years ago, you could get this book from Amazon. Now, since it's out of print, but there are other ways of getting the book. They even have a Kindle version. I tried it, a sample, and surprisingly, it's readable, which is really surprising. Because usually Kindle versions of scientific books are completely useless. We are not going to cover the whole program. I mean, all the chapters of the book, only this. Okay, this is just for continuous groups. That's another thing. Okay, we're not going to use. There are other books. One book which is very nice is all book is also by a Russian. I mean, Russians, when they write about applied mathematics, are very good because they are very well organized. They are very concise. They don't give you unnecessary material. Everything is very rational and so very easy to read. So this is the case of also with Lyubarsky. Lyubarsky goes farther than the previous book. It's a very old book. It's from 1960, but there are reprints and there are old copies. That's the book I learned with, so I really love it. I like it very much. And it's a very complete book. It's a very serious book. Then there is this much more modern book. This one has an advantage. The advantage that it has many applications. This one has also some applications, but not as many. It has many applications. It has all, except for topological quantum chemistry and band representations and things like that, I don't think you will find on any textbook. on group theory is still too new, the stuff. You have all the other applications here. I haven't read it, so I cannot tell you whether it is good or not. A student of mine has read it, and he said that, well, that it was nice because of the examples and that, okay? This one is in print, you can get it from Amazon, for instance. And this one is a very useful book, Bradley and Krankner, The Mathematical Theory of Symmetry in Solids, and for many years was the best book for group theory tables. Now with the Bilbao crystallographic server, well, it's much easier to use the Bilbao crystallographic server than using the tables in this book, but they're still useful. And the book is excellent. It really goes very deep. It goes to magnetic groups, to everything. Everything is there. But it's not at all a book for beginners. I never heard of anybody learning group theory from this book. Probably he or she will die. It's really a tough book. But it's a very good book for practitioners. If you use group theory in your thesis, you should have this book also. Even if you don't read everything, it has so much material and it's very good. Okay. So let me comment, since I'm going. Let's see. This is already 1 hour. Okay. So I think I'll move into the second lecture. Probably I'm going so fast because nobody asked anything. So maybe it would be a good idea if somebody asks anything or makes a comment or anything. Let's see. Okay.
I would have a question on the representation definition. Perhaps you can show the slide.
Yes, which one? Okay, on the representation. Yeah, okay. The one where I define the representation.
Yes.
Yeah. Okay, let me see. Yes, just a minute. I have to share again. Well, okay. Let me just share it this way. Okay. Can you see it?
Yes.
Yes. Okay.
There you wrote that the only thing that T has to fulfill is that if G1 composed with G2 is G3, then also the representation of G1 times representation of G2 must be representation of G3.
Yeah. For all the elements of the group and for all possible compositions. Okay.
Okay. Yes. And you write there only if the left side is true, then also the right side is true. But shouldn't there be some kind of equal thing or other condition for T? Because what I thought of, if it's only this condition, you could just choose T to be the identity on every element, which would be not a good choice. But that would fulfill this statement because identity times identity is always identity.
Yes.
It of course has nothing to do with the group elements, but it would still fulfill this equation.
Okay, yeah, that's a very good question. Let me see. But in fact, there is nothing wrong with the identity representation, I must tell you. I don't know why you don't like it. How do I do this? Let me see. Let me see. Yes. In fact, here, A1, can you see the slide? Is the vibrational spectrum?
Yes.
Yes. A1 is the identity representation. Okay, every group has a one-dimensional representation, which is irreducible representation, which is the identity representation. It's a very important representation, and it's always a building block. For instance, for the vector representation, it's true that the vector representation is different, very different from the, let's see, what is the vector representation, from the identity representation. But look at this block, 1, 1, 1, 1, 1, 1.
Yes, with this I'm fine. The point is that with this definition of representation, you could choose for all of those 6 matrices the identity matrix.
Yes, but you can also choose other things. That's the point. That's not the only choice. There are infinitely many choices. Okay, so representation is any mapping between the group and the elements that respect this constraint. So you are right. I mean, there is always a trivial solution, but this is like a differential equation. I mean, differential equation, a partial differential equation has all kinds of solutions. Some of them might be very trivial, but this doesn't mean that the equation is useless. And it is the same thing here. I mean, this definition, this the only constraint, has infinitely many solutions. The vector representation is another one solution. There are infinitely many. And one solution is always just assigning a one by one matrix or an identity matrix in any dimension to each of them. Okay. I don't know if that answers your question or.
I think the point that I don't like about that is if you choose that representation, you have no way of mapping back. So you have no inverse. So if you know the matrix representation, I think you should be able to get back to the group element, but with this representation, you aren't. So the question is there a restriction like you have to have a mapping back or a way to map back?
You have to have a what, sorry?
Do you have, I mean, by that you have a way to get for every group element a representation element, so like a matrix. Do you have, does it have to be like bijective? So do you have to have a way to find an inverse? So to every matrix you can get back to the group element.
No, but that's just no, of course. I mean, that's just this. I mean, this should be true for the matrices. In particular, there should be for okay. For the inverse element is the inverse matrix. Okay. I mean, if you read the books and some of the things I'll tell you, there are many things like the things that you're asking now. Okay. Maybe what you have in mind is also the following thing. There is something which is called a faithful representation. A faithful representation is a representation that assigns different matrices or operators to different group elements. Okay. In that sense, if you know the matrix, you know which element it is. That's a faithful representation. Some representations are faithful, but not all of them. For instance, in this case, this is a faithful representation because you use different matrices for all the group elements, okay? But, okay, this is our first contact. So all you should know so far is that you have matrices and they have to satisfy this constraint. If they do, you have a representation, okay?
Okay, yes, thanks. That answers my question.
Okay. Any other questions?
I have a question. Yes. When we were telling that some molecules are Raman or infrared wave active, how can we know that from group theory? I didn't understand well that part.
Okay, no, it's, I mean, you shouldn't understand it. I mean,
yes.
It would be a miracle if you had understood it because okay. I haven't explained it at all. Okay. No. Okay, now let me go to the program of the course. Okay, where is that? Okay, and let me share. Am I sharing still? No. Okay. Okay. Yeah, let me comment on what we are going to see, because some of your questions have to do with the future, with what we are going to see. Today was just a first contact. You have some intuitive idea of what a representation is, and basically of the usefulness of representations and the usefulness of irreducible representations. They give you the shape of the spectrum, how many different frequencies, what the genus is. I have mentioned that they also give you the activity of molecules. These are just selection rules, in fact. Basically, if something is active, it's because under, for instance, infrared radiation, you can move from one state to another state. Okay. Now, to do that, you have to go to 3 and 4. Okay. In the first lecture that I'm going to start today, because we still have 20 minutes left, we'll learn something about the irreducible representations, and we'll learn how to compute what I have shown you today. And now, once you know both representations, you have to be able to take products of representations. Okay, these are operations with representations. And from this, in this lecture, you will understand Wigner's theorem. You will understand why the multiplicity is related with the number of different frequencies, and why the degeneracy is related with the dimension. Okay. Now, by taking, this is just by taking products of 2 representations. By taking products of 3 or more representations, you will be able to understand how we get the rules for infrared and Raman activity, selection rules, okay? But of course, I mean, you have no ground to understand what I told you today about infrared and Raman activity. You need all of this stuff to understand this, okay? You need 3 more lectures, okay? Then, all of this is about molecules and vibrations of molecules. So it's just about the mechanical representation, which is called, okay? Then we will include electron orbitals in atoms, and we'll include spin. We need something which are called double valued representations or double groups. And then we'll see how you can use group theory to study the splitting of atomic orbitals in crystals. It will be the application. It can be used for many more things, okay? All of this, I mean, atoms, the group symmetries for atoms are point groups, because if you translate an atom, you immediately notice that you have translated the atom. That's never a symmetry of an atom, okay? You only have to keep the center of the atom fixed. And by definition, this is a point group, okay? So all of these, although they are general, they can be applied for any other thing, we'll use only for point groups, okay? Then we'll have to study space groups, and we'll study crystals. Now, in a crystal, an atom can never be invariant under translation. However, if you have many atoms, like in a crystal, an atom moves to the position of another atom, and you don't know there has been any change. So in order to have translation symmetry or space groups are combinations in some sense of rotations and translations, then you really need to have crystals. Okay. And then we'll use this theory to apply this to the electron bands. We'll take a concrete example. You'll see how how the irreducible representations are assigned to all the bands. We'll see how group theory and irreducible representations constrain the possible degeneracies. When you have crossings, which crossings are symmetry protected, that probably you have heard a lot of times. All these things you will understand deeply. And then we'll see the compatibility relations which control the connectivity of the bands. Until 4 or 5 years ago, this was not very important. Now this is extremely important, because that's the bridge between group theory, symmetry, and topology. And that will be the object of the last lecture, okay? So we have like 15 minutes left. I'm going to start with the next group of slides. Let me see. If there are not any more questions, Chiara, you have a question for some reason that you appear in my screen? Well, so, no, yeah. Well, okay. So let me share. screen. Okay. So now we go to the second chapter, second topic, irreducible representation as building blocks. Okay. Basically, the aim of this is to compute, to obtain this result, okay, this set of slides. We had to do some group theory computations. These were some representations that have a physical interpretation, mechanical, vector, rotational, vibrational. These are abstract representations which have, these are abstract, these are just possible representations, possible mappings between matrices and the elements of the group that respect the structure of the group, that respect the composition law. And then we have seen that from the multiplicities, we find the number of different frequencies, and from the dimension, the degeneracy of each of these frequencies. Okay. Well, I think I'll have to fix this in all the slides. I don't know why this is happening. The vector representation tells you how ordinary vector transform. And we saw, well, we have to use some particular set of axes. I'm repeating all of this because the first time I gave the course, this corresponds to 2 different days. So I had to remind people of what I had said in the previous lecture. This is the vector representation. And now this is new. We are going to see the difference between reducible and irreducible representations. This is a very simple example. Look at this. You see that this, for the vector representation, the matrices have a block structure. They are all block diagonal. It means that I can construct all matrices, not just one of them, all of them, by taking 2 by 2 blocks and then 1 by 1 blocks. So the vector, when this happens, the vector representation decomposes into 2, well, in this case, into 2 irreducible representations, which are A1 and E. See what I mean by this. These are all 3 by 3 matrices, and these 3 by 3 matrices satisfy the composition rule. For instance, if I multiply this times this times this, I have to obtain this, because if I rotate 120 to the right and then 120 to the left, I haven't done anything. So this matrix is the inverse of this, and you can check that this is true. Okay, so this is a 3 by 3 representation. But now you see that they have some blocks, diagonal blocks, and these diagonal blocks, this is a 2 by 2 representation. I'm going to show this in a minute, and this is a 1 by 1 representation. This I say by saying that the vector representation, which tells you how X, Y, and Z coordinates transform, decomposes into a one-dimensional representation, which tells you how the Z component transforms, plus a two-dimensional representation that tells you how X and Y transform. You see that these 2 by 2 matrices act on the X, Y, and Y components, and this acts on the Z components. So we say that the vector representation is reducible. Whenever this happens, whenever you can take the matrices and decompose into block diagonal form, and with exactly the same block diagonal form for all the elements, okay? I mean, obviously this I can decompose in 3, one block, one block, one block, but this is only true for this or for this, not for the others. The decomposition has to be valid for all the matrix elements, okay? When this happens, we say that the representation is reducible. When this is impossible, we say that the representation is irreducible, okay? In this case, these blocks cannot be reduced anymore, I cannot write these blocks in a diagonal and in a block diagonal form. So I say that the reducible representation V vector decomposes into the sum of two irreducible representations, one with dimension 1 and another with dimension 2. So now at least you understand when I wrote in the previous slide, I wrote this V equal to A1 plus E. That's what this means. I told you that this is not an addition of matrices, because this is one-dimensional, this is two-dimensional, this is three-dimensional. What this really means is just this, that I can write this thing in this block diagonal form, okay? And that's the way I write it formally, because this is the Z component and this is the XY component. I can be a little bit more rigorous mathematically. These zeros mean, I mean, you see there are zeros here. There are zeros here and here for all of them. This means that this three-dimensional space spanned by the three coordinates has two subspaces. One subspace for the Z component, which is one-dimensional, and another subspace for the XY components, which are two-dimensional. And these two spaces are invariant. One says that I have an invariant subspace if there is no operator that takes you out of the space, okay? The space is stable against all the operations. For instance, assume that you take a vector which is in the E direction. Physically, this means that this is a vector which is on the plane. Okay, it's a vector which is on the plane. Obviously, if I start with a vector which is on the XY plane, the XY plane is this, That is the plane of the basis of the molecule. Obviously, if I rotate it, it remains in the same subspace, the XY subspace. If I reflect it by these mirrors, it also remains in that subspace. So that is an invariant subspace. The same thing happens with the axis Z. If I take a vector pointing in the Z direction, if I rotate it, doesn't change, doesn't move away from the Z direction. And if I reflect it, it doesn't move away from the Z direction. And that's exactly what happens. If I take a vector here, 0, 0, whatever you want, 3. If I add with all these elements, that's still a vector which is in the Z subspace. The only non-zero component is the Z component. If I take a vector which is originally XY 0, this will always be a vector with XY components different from 0 and this one equal to 0. So in more mathematical way, I can say that the representation is reducible if the space has invariant subspaces, in the sense that I told you, that no operator takes a vector of the invariant subspace away from the invariant subspace, okay? So that's in a more mathematical way, the idea of reducibility and irreducibility. Here, it seems that they are not invariant subspaces, but you shouldn't trust what you see. Okay, I mean, obviously, here there are no blocks, there are no diagonal blocks. Okay, if I take a vector in the X direction and I rotate it, it moves away from the X direction. If I take a reflection, which is not along the vector, it also moves away. So obviously, well, it seems that there are no invariant subspaces. So this is suggesting that this representation is really irreducible, and it is. Okay. Okay. Before I continue, is that perfectly clear? Anybody wants to ask any question? Because this is a very important concept.
Juan Luis, one question.
Yeah.
Here, I see that it's clear that we can do this that it's reducible because we can decompose our representation in these two. But this here is obvious because I don't have a coupling between the zeta direction with the x and y.
Yes.
But for example, it could be possible that I couldn't do this block, diagonal blocks, the separation that you did here. And still you have
yes. And still be reducible. Yes, that's a very good question. And this has to do with the next slide. Okay. I'm going to show you another representation of the vector group. I mean, his question is, in this case, it's obvious that I have this block diagonal form. If I don't see a block diagonal form, can I conclude that it's not reducible? Well, no. Look at this. Well, okay, I have, okay. No. This is what I wanted to show you. Look at this. This is another representation of the vector of the, sorry, of the C3b group. It's the same group, but these are different matrices. Here, there are no blocks. So you could conclude that this is irreducible because there are no blocks, that there are no invariant subspaces. However, your conclusion would be wrong. This representation is actually reducible. In fact, this representation is the same. It's exactly this representation. It's the vector representation. The only thing that I have used a perverse choice of axis. In fact, I have used this axis. So this is still reducible, but basically, instead of using x, y on the plane and z perpendicular to the plane, I have used the x-axis is the same as before, but I have applied a 45 degrees rotation to the y and z axis. And the representation is reducible. So this means that what can you do? You construct your matrices. How do you know whether the thing is reducible or not? How do you know how to reduce it? Okay, that's where you begin to need the machinery, the formal machinery of group theory. Okay, so far, I mean, you can construct these matrices. I mean, a first-year student can construct these matrices in any basis and things like that. Another thing is, which is very hard if you don't know any group theory, is how do you know whether these matrices can be decomposed or not? How do you know whether there are invariant subspaces? And now, and this is the last concept we're going to see, is the concept of equivalent representations. Two representations, T1 and T2 of a group, are said to be equivalent if there is a non-singular matrix A such that they are related by conjugation. Okay? There is a typo here. This would be T2 here, and here it should be T1. Okay? There's a typo. I'll correct this before I give you the slides. So you have T1 and T2. Well, if you can take the matrices of T1 and apply a conjugation operation by a matrix, by a non-singular matrix, and you obtain T2, then they are equivalent representations. Concretely, in our case, the W matrices, which didn't look at all reducible, were obtained, and you will check that in one exercise next time, by this transformation matrix. This is the transformation matrix that takes you from the original axis, which was a rational choice of axis, with a perverse choice of axis. You see, the x-axis is still the x-axis, but this represents a rotation, 45 degrees rotation between the x and y-axis, okay? And this will be explicitly the change of coordinates. If u is the coordinates x, y, z, this is this change of coordinates, okay? Which is a rotation. So this means that if you want to know whether a representation is reducible or reducible, what can you do? Can you start trying infinitely many transformation matrices to see if you manage to turn it into a block diagonal form. I mean, this is completely hopeless. I mean, just by looking at this, I don't think any of us would be able to guess that there is a transformation that take us to this nice set of matrices. Okay, that's impossible. Computationally, that's crazy. Okay, so then you need group theory to answer this. The concept that we need is the concept of characters, but this already 15 past 1, so we'll stop here. We'll continue next time with the theory of characters. Okay, so let's stop.
Thank you very much, Juan Luis.
Okay.
Are there more questions?
I have one question. It's about, right now we found one representation which is not reducible in this example. But can we say, okay, can we find a representation which is irreducible for this case? Or can we say from the beginning, this does not exist?
Okay. Yes, well, that has to do with what we are going to see in next lecture. Basically, the number of irreducible representations is always finite for finite groups, okay? Up to equivalence, okay? I mean, if you give me a representation, just by choosing different transformation matrices A, I can always write infinitely many sets of matrices. But this is, I'm just cheating. I'm just writing your matrices in a different set of axes, okay? So up to equivalence, the number of irreducible representations is always finite. In fact, is always equal to the number of classes in the group, okay? I'll tell you next time what a class is. And so that's the good thing about discrete groups or groups with a finite number of elements, and the number of representations is finite. There are very few usually. For instance, this group, the TD, only has 1, 2, 3, 5 irreducible representations with dimensions 1, 2, and 3. Any other matrix, no matter how huge, how large, how complicated, is always an integral linear combination of this, after a change of basis, of course. Okay, you have to make a change of basis to make this obvious. Like the vector representation was A1 plus E. And I'm going to give you the results. I'm going to give you a few theorems. I won't prove the theorems. To really understand formally the whole thing, to go through all the proofs, you need to read 2 or 3 chapters from the books I recommend you, okay? And I certainly recommend you to do it if you are planning to use group theory seriously for your work. If you just want to be able to understand what people say in group theory, you don't need, and even to work, I mean, I don't remember any of the proofs. I will be hard pressed to give you a proof of any theorem. I don't even remember most of the theorems. I only remember the theorems that I use in my work, okay? But even so, when I was a student, I spent 3 months or so learning from the book by Lubarsky, okay? That gave me confidence that what I do, I know what I'm doing, okay? So I don't know if that answers your question.
I will see next time.
Okay,
Thanks.
yeah, you have to wait till next time. Okay. So are there any other questions? If not, we'll meet next week at the same time as today. Okay.
Yes, please join the Zoom room a bit earlier, that we can start at 11:45. Okay, thank you.